Look at this. An entire grade boundary literally wiped out, all because of one disastrous, yet completely avoidable, mistake on a Hooke's Law practical data question. Seriously, it hurts to see. But hey, in the next 60 seconds, I'm going to show you exactly how to rescue a failing answer just like this one and turn a massive physics misstep into guaranteed marks. Let's get right into it.
0 out of 4 marks. Yeah, that's the immediate, painful reality of losing maximum points on a practical data question. It's a huge confidence shock, right? And the crazy part is, it usually happens because of a simple, fatal oversight in how you're reading a data table or interpreting a graph during your Cambridge IGCSE physics exam. The margins for error here are incredibly slim. Examiners aren't just looking for general knowledge, they are hunting for specific, undeniable evidence that you actually get it. Okay, let's dive into this. Take a look at this classic, massively flawed student answer. The student just wrote, "The spring got longer." I mean, it sounds logical, right? It's exactly what you see with your own eyes in the lab when you hang a weight on a spring. But look at all that blank space waiting for a real answer. That generic phrase completely fails the mark scheme. Why? Because it lacks any mathematical or scientific precision. In physics, we don't just describe what we see, we quantify it. Saying it got longer is way too conversational. The examiner needs hardcore proof that you understand the mechanics of why and exactly how much it stretched. To really understand why an answer like that earns absolute 0, we need to ground ourselves in the exact syllabus. We're looking at Section 4, turning effects, which covers moments and the center of gravity, and Section 5, stretching springs. And get this, examiners report that over 40% of students lose marks here. Not because they don't know the physics, no, but because they use everyday language instead of syllabus-specific terminology. You've kind of got to treat this like you're learning a completely different vocabulary. So why does just memorizing the textbook totally fail you when you're actually analyzing data tables and graphs? Well, it's because the mark scheme brutally penalizes practical mistakes. I'm talking about things like missing units in your final calculation or rounding your numbers way too early, which, by the way, cascades into a massive gradient error later on. Throwing in vague explanations or citing the wrong experimental variables will instantly tank your score. And if you write weak practical improvements, like, I don't know, just saying be more careful or draw conclusions that totally ignore the data, those marks disappear in a flash. The exam is testing your analytical rigor, not just your memory. To secure those high-mark quick wins, you need a bulletproof, systematic approach. Enter our proprietary 4-step exam framework. Step 1, the concept. Identify the fundamental physics principle at play. Step 2, the evidence or data. Pull the exact numbers straight from the table or graph to back up your claim. Step 3, scientific reasoning. Connect the data to the concept using a formula or physical law. And finally, Step 4, lock it in with exact examiner wording. This structure literally forces you to answer exactly how the grading rubric demands. 0 room for ambiguity. All right, let's apply the first 2 steps of that framework to upgrade our failing answer. Instead of the vague, everyday observation that the spring got longer, we inject precise physics terminology. The corrected concept becomes extension is directly proportional to load. Boom. Suddenly, you aren't just describing a physical event, you are stating a definitive mathematical relationship. You're telling the examiner that as the force increases, the extension increases at a constant rate, which, by the way, would plot as a perfectly straight line through the origin on a graph. Now you are finally speaking the examiner's language. And you know, this brilliantly illustrates the leap you need to make for syllabus section 5.3, the limit of proportionality and the spring constant. At this level, you aren't just stretching a spring and watching it bounce around. You're expected to mathematically analyze the relationship and actually calculate that spring constant directly from your experimental data points. You need to confidently use the equation force equals spring constant times extension, F equals kx, and rearrange it to find k. That spring constant tells us the stiffness of the spring. It literally tells you exactly how many newtons of force are required to stretch it by 1 meter. This is where the real physics happens. But here is the catch. In just a moment, I'm going to show you the hidden examiner clue in the data that changes this calculation completely. I'm telling you, it is the single trap that trips up even the absolute most prepared, top-tier students. But first, you really need the framework that makes that clue absolutely obvious the second you glance at a table. You got to know what to look for before you ever even pick up your calculator. So let's do a quick interactive challenge. Take a look at this mock data table mapping extension against load. I want you to pause this explainer right now. Seriously, pause it. Can you spot the deliberate anomaly hiding in these data points? Track the progression of the extension as the load increases, and look really closely at the table header. What crucial design element is completely missing that would cost you an instant mark in a practical paper? Take a guess. Okay, did you spot it? If you notice the data points suddenly spiking out of a straight line pattern at the bottom, you found our hidden clue. And this brings us to the core concept students miss when their graph gradients go horribly wrong, the limit of proportionality. By definition, this is the exact point beyond which Hooke's law is no longer true when stretching a material. The spring actually undergoes plastic deformation instead of elastic deformation, which basically means it won't return to its original shape. If you blindly use data points past this limit to calculate your spring constant, your entire equation collapses. Why? Because the relationship is no longer proportional. You must only use the data points before this limit. Let's escalate this to a slightly harder scenario. To secure top bands in these questions, you absolutely must perform final practical checks. Have you clearly checked your apparatus setup? Are your safety protocols stated? Like, are you wearing safety goggles to protect your eyes from snapping wires under high tension? And what about that missing table header we just talked about? Have you checked for missing units, like making sure extension actually has millimeters written next to it? Did you use the correct significant figures, read the ruler at eye level to avoid parallax error, and account for uncertainties? These rigorous checks prove to the examiner that your conclusions rely on accuracy, not just guesswork. Which brings us to the ultimate transformation. We are going to take everything we've just discussed and wrap it into one perfect, highly scored package, the examiner-style correction. So the crucial point here is comparing these two approaches. Contrast that flawed, generic scribbling that earns literally 0 marks with a true top-band masterclass. Look at how the winning answer applies our framework. First, it starts by stating the exact equation, k equals f over x. Then it features substituted values, calculating the gradient using, for example, 50 newtons divided by 0.1 meters to get 500 dynes. And crucially, the correct units, newtons per meter, are included right there in the final answer. It explicitly identifies the anomalies past the limit of proportionality and explains exactly why those specific points were excluded from the gradient calculation. Finally, it fulfills the command words perfectly with exam-safe terminology. Guys, that is exactly how you turn a failing grade into maximum marks. So, you now have the exact framework to secure maximum marks on practical data questions. You know how to check for reliability, spot anomalies, and use the right terminology for Hooke's law and moments. But here is a massive, unresolved problem. What if you run out of time? Knowing the perfect 4-step answer doesn't help you at all if the exam timer runs out before you can physically write it down. Speed and precision have to work together, and honestly, pacing is exactly where most students fall apart in the final stretch. The full rescue kit to conquer that intense exam timing pressure continues in our next explainer, where we cover the timed answer writing system. Watching that is the mandatory next step to ensure you never, ever leave blank lines on your paper again. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSES to excel in your Cambridge examinations. See you in the next explainer.